Meta.
As you know, my name is David. I am the creator and host of CVS. In today's episode of Meta, I'm going to talk about solving induction by reduction deduction. The Scottish Enlightenment philosopher of the 18th century, David Hume, made famous this problem of induction, which haunts the natural sciences to a certain extent. But luckily, there's more to science than induction, this empirical bottom-up method of observing patterns in nature and trying to come up with models that will allow us to predict. Based on what these patterns are, in theory, we can predict how reality will behave in similar circumstances. This is a situation which is very messy and complicated, and if we look at the history of the hard sciences, physics and whatnot, we see that there is a lot of groping in the dark. Even if we limit ourselves to Newtonian physics, there's a lot of groping and readjustments of models that need to be made because of this problem of induction. We cannot ever be certain that the model that we have of the pattern in nature is accurate enough, and often it is not accurate enough. And if we bring the new physics into it, and quantum physics, of course, our observations at the quantum level have really made us scramble to readapt our models so that we can make predictions. That's what science is about, making reliable predictions. We need to adjust our models to reality, not the other way around. This whole notion of indeterminacy is a philosophical game. It has nothing to do with the reality of nature and of science. Science is trying to model reality. It's not the other way around. Our observations do affect nature. Obviously, when I poke my stick into the pond to try to figure out its depth, obviously I'm moving stuff around. It's the same thing with quantum physics. When we blast photons or electrons into these delicate systems, obviously we're stirring things up. This is not rocket science. This is not woo-woo. This is not fairy dust. This is not magic. This is certainly not a way for atheists to say, oh, I am free. No, this is reality. We're bumping up against reality. We're bumping up against our hard limitations. And if anyone wants to debate me on indeterminacy, the uncertainty principle, or anything like that, these are philosophical interpretations. You are free to have your absurd Copenhagen interpretation and all the rest if you like, but I am a realist. I believe that reality is real and that there's a sufficient reason for every mechanism, including mechanisms which we have labeled quote-unquote indeterminate or quote-unquote random, and so on and so forth. But in any case, today I'm going to talk about two simple examples that show how reduction deduction solves the problem of induction. And what I mean by reduction deduction is simply the application of this technique called reduction to absurdity, which is very popular. It's used throughout philosophy. It's universally accepted as a valid deductive reasoning technique. It was used in Anselm's ontological argument, to cite one famous example, and it's used all over the place. I use it all the time. I use it in combination with extremism, where you push the limits. If someone wants to take a position on a spectrum, I like to move along that spectrum to the extreme limits and to find out what gives, what breaks, and what absurdities and contradictions we can find at either end of that given spectrum. For example, with atheism, materialistic atheism, I like to push that to its limit. Well, what does it mean if every effect is natural and every natural effect has exclusively natural causes? What does that mean? And so this will bring us to hard determinism, and from there it is self-evident that atheism is false. So for my first example, I'd like to talk about gravity. There was a common sense intuition, conventional wisdom, that of course a bowling ball will fall from the top of the tower faster than a feather. And that is true because of air resistance and things like that. But people started experimenting, and they started to discover that it seems like in a vacuum, to the extent that we're able to create a vacuum, perhaps the acceleration due to gravity is independent of mass. And this was quite counterintuitive. So a lot of time and money and effort went into these experiments, and I thank God for empirical science. But there's another side to science, which is deductive reasoning. It costs less money, it's more fun, and we can do it from the comfort of our living room. So for the sake of this experiment, I want you to picture two horseshoes a black horseshoe and a white horseshoe. The black horseshoe is made out of a very dense iron, and the white horseshoe is made out of a very light styrofoam. So we set up a vacuum in our mind's eye in this laboratory of the mind. We hold the two horseshoes up their centers of gravity 100 meters from the ground exactly. They're side by side, but they're not touching, and we release them at precisely the same moment. And for the sake of this thought experiment, we assume the opposite of our thesis that we're trying to prove, namely the thesis that their acceleration due to gravity will be independent of their masses. So the opposite of that is to assume that their acceleration due to gravity will be dependent on their masses, and in a way that is directly proportional, meaning that the more massive one will fall to the ground more quickly. So we release them from the same height at precisely the same moment, using this assumption that the massive one will fall more quickly, and lo and behold, in our thought experiment, that's what happens. The black iron horseshoe clunks to the floor well ahead of the light white styrofoam horseshoe. That was a great success. There's applause in the laboratory, and we move on to stage 2. This is a 3-stage experiment, and by the time we reach stage 3, you'll see why there's a contradiction that we need to reject, and why our thesis is in fact 100% certain. So stage 1 was a success. Let's move on to stage 2 of our experiment. We pick up these exact objects. They are undamaged, they have not been modified in any way, and we bring them up to 100 meters once again. Their centers of gravity are at precisely 100 meters from the floor in this giant vacuum chamber, and they are not touching. The difference is that they are now placed on the same vertical axis, meaning that as they fall, they will come into contact with each other. The heavy black horseshoe made of iron is facing downward like an upside down U, and it is over top of the white light styrofoam horseshoe, which is in a U shape, upright U. So when we release them, even though they're falling from the same height, once again, and they're not touching, we can see that inevitably the black iron horseshoe, which is on top, will fall into the slower moving white styrofoam horseshoe. So they are going to come into contact. Newton's laws of motion will introduce action-reaction drag, where the lighter one will impede the heavier one, and the heavier one will drag the white one, and they will together have somewhere between the minimum acceleration of the white one on its own and the maximum acceleration of the black horseshoe on its own. Because they are coming into contact with each other and they are not able to shake free from each other because of their hook-like shapes, they are forced to interact with each other and to give this resulting intermediate rate of acceleration due to gravity. So for stage 3, I want you to pick up your two horseshoes, place them exactly as they were in stage 2 of our experiment, hovering close to each other but not yet touching. As they fall, they will come into contact with each other. They will have an intermediate rate of acceleration relative to the first stage of the experiment. But to make this more interesting, let's place a third object in the chamber. This third object is equivalent in mass and volume to the combined horseshoes, which are two independent objects. So what happens in this race to the finish line as they both fall? The one pair of independent objects which are not touching, whose centers of gravity are identically placed at that 100 meter mark, and this new object, which is sort of a monster composed of what looks like the exact same two objects, but now it's one object, and because the total mass of this new Frankenstein object is greater than even the black iron horseshoe, it is bound to win the race. So clearly what we have here is a contradiction, because the only thing that distinguishes the Frankenstein horseshoes from the pair of independent horseshoes is that one is considered one object and the other is considered two separate objects. But there is absolutely no difference in volume, there is no difference in mass, and yet there is a difference in the acceleration due to gravity, because we have assumed wrongly that the acceleration due to gravity is dependent on mass. Therefore, because when we assume that the acceleration due to gravity is dependent on mass, we arrive at a contradiction, we are able to, with 100% certainty, conclude that our axiomatic assumption is false. And we must therefore conclude with 100% certainty that the acceleration due to gravity is in fact independent of the mass of the objects. And we didn't even have to leave the comfort of our living rooms. We need to submit our wills and our minds to this fact of reality. It's devastating to those atheists that like to hide behind agnosticism and they like to use empirical science as a bludgeon to bludgeon theists for making truth claims that they have no right to make, when in fact we do not have to have recourse to empirical science, the laboratory, the experiments. I'm not downplaying the value of empirical science. I thank God for empirical science, and I thank the Catholic Church, frankly, for empirical science. Now, let's move on to my second example, which has to do with the famous proof that 1 + 1 = 2. This was published in 1910 by Russell and Whitehead in their famous work Principia Mathematica, and there are several hundred pages dedicated to setting up the stage for the proof, the logical proof that 1 + 1 indeed does equal 2. Russell and Whitehead's work is deductive in nature. That's the whole point. They are logicians trying to prove a point about the logical basis of mathematics, that it is a system that is logically provable and that is logically self-consistent. And so I have no bone to pick with this approach. But there's a reduction to absurdity approach, which is faster, cleaner, and more handy for those of us that aren't professional logicians and professional mathematicians. When I go to the grocery store and the cashier gives me the wrong change, I'm able to show her using a reduction to absurdity that 1 + 1 does in fact equal 2. And if she wants to pull out the proof that 1 = 2, which is floating around out there, which involves a division by 0, I don't need to use fancy mathematical arguments. I can simply use quickly and easily a reduction to absurdity to prove to her that 1 does not equal 2 and that 1 + 1 does equal 2. If I want to prove that 1 does not equal 2, then I have to assume the opposite, that 1 does equal 2. And when I assume that 1 does equal 2, then if we look at the number 3 is 1 + 2, but 1 = 2, therefore 3 = 1 + 1, because 2 = 1, therefore 1 + 2 = 1 + 1, therefore 3, which equals 1 + 2, equals 1 + 1, and therefore 3 = 2. But 3 also equals 1, because 1 = 2, therefore 1 = 2, and 1 = 3. A logical contradiction. So I hope you found this interesting and useful, that we can know reality through reasoning. It's a rationalistic approach. There are certain forms of rationalism that the church has condemned. There are other forms of rationalism which are natural, wholesome, healthy, and reasonable in the natural sciences, the hard sciences, and philosophy, and even mathematics. So that's it. Talk to you soon. Take care. God bless.